Do you know that there is such a device that transfers heat using phase change process and with a very minimal thermal gradient? Hi, my name is Zakariae Maatallah. I'm an energy engineer and PhD student from the University of Science and Technology of Beni, Mellal, and in this presentation we will try to investigate the design of the future heat pipe for aerospace application. So in order to present this topic chronologically, the outline will be structured in this manner, starting with the motivation behind this work, the general context, and for the last but not the least, investigating micro heat pipe system, and finally we'll make a conclusion. In the recent years, electrical equipments are becoming smaller and faster, which makes them generate a lot of amount of heat. So there was a lot of recent emphasis on heat dissipation. Microheat pipe is being looked as one of the emerging technologies in thermal cooling and has a set of features which can we classify them as follows. High thermal conductivity compared to the standard thermal conduction process, very low thermal gradient to transport heat, it's a passive device, relatively small in size and weight also. Makes it desirable component for cooling small devices. This presentation will focus to give a better understanding of the heat exchangers by two-phase process and also the path we'll pursue in our PhD project in order to design the future cooling device for the aerospace application. So to do such a thing, it's necessary to start investigating the heat pipes for its small scale, micro heat pipe precisely, and then upgrade it to the other scales in order to understand deeply what's going on inside of it and how and what are the limitations that governs those heat exchangers in our real life. There is a lot of families of heat pipes, but the working process is a little bit the same with some small exceptions. The first one is the capillary heat pipe, which is a heat transfer device that combines the principles of both thermal conductivity and phase transition to effectively transfer heat between two solid interfaces. The heat input vaporizes the liquid working fluid inside the weak structure in the evaporator section. Then this latent heat flows toward the condenser to release heat to the cold environment. Then the liquid condensate returns back to the evaporator using this porous media named weak structure, which provides the sufficient capillary pressure to make sure that the liquid arrives to the evaporator section so that the evaporation condensation process still continuously operates. Another type of heat pipe called thermosiphon, which has the same operating process, but the only difference is that the liquid is returning back by the gravity without any use of such a capillary structure. Loop heat pipe possesses all the main advantages of the conventional heat pipes, but owing to the original design and special properties of the capillary structure are capable of transferring heat efficiency for distances up to several meters at any orientation in the gravity field, which makes a desirable device for thermal cooling in aerospace application. Here we have some applications of the heat pipes family. Thermal management of electronics. We can use heat pipes to cool processors in the phones or laptops. Thermosiphons are used in solar collectors. Loop heat pipes are used to cool satellites, and finally heat pipes also are used in the heat, ventilation and air conditioning systems. Micro heat pipe system. Micro heat pipe is a non-circular channel with sharp edges to provide the sufficient driven pressure to the liquid by the increase of its main curvature at those edges from the condenser to the evaporation, so that the liquid arrives to the evaporation section. We have the animation of how the micro heat pipes work. They are used in several systems like sensors, electronic watches, temperature warning systems. Also are used to increase the inherent thermal conductivity of silicon for such a task. The aim of this presentation is to prescribe the main path of the PhD project by understanding the heat pipes in the microscale, to really get a comprehensive knowledge of the phenomena that could occur like Marangoni effects due to the large change in the surface tension in a small tiny time. Also to master the limitations of the heat pipes in general, which could occur when a bad operation of the microheat pipe is made, like dry out or flooding, as an example, or when the vapor reaches its sonic velocity, and this kind of limitations we call it sonic limit. Thank you for your attention.